right, so welcome to the first online or virtual lesson for ME555. Today we're going to be dealing with basically pumps and pump selection. So fluid movers in general, classified by a few different things. So as I mentioned, we have pumps. We also have things like fans, blowers, and compressors. So depending on what fluid these things are actually moving, so there's a big distinction between how you move a liquid compared to how you move a gas. So pumps generally are for moving liquids, whereas fans and blowers, compressors generally involve air or gases. Another categorization is either by flow or pressure. So is this something that you're adding a lot of pressure to the system, in which case you have fairly high pressure drop or pressure gain with relatively low flow rate, or is it something where you have a relatively high flow rate but with a relatively low pressure? And last thing is by mechanism. So how is this actually accomplishing moving the fluid? Is it some sort of positive displacement mechanism, piston, rotary screw, scroll, root, thing of that nature? Or is it a velocity recovery system? So centrifugal, radial, axial pumps or ejector type pumps. And the way these things are analyzed are through what's called affinity laws. So these are similarity relationships based on dimensional analysis. So you want to find dimensionless numbers associated with all the flow parameters. And with that, it basically tells you how things are going to react when you change things. So these are not exact relationships. It's not an exact equation that tell you what is this under certain scenarios. It's more of what happens when I change something. So if I double the flow rate, what's going to happen? Now usually what I want to deal with is the two things I can change on a pump are its rotational speed. So I can make it run faster or slower, and that has to deal with the rotational speed of the impeller inside the pump. The other thing I can do is basically just change my pump to a larger or smaller diameter pump. So those are generally the two things that are my independent variables essentially. And then with that, I get some dependent variables. So what happens to things like flow rate, things like head loss, things like pressure or power? How do those things react when I change the diameter or rotational speed? So if I look at changing the rotational speed, so for a given diameter, so diameter stays constant. If I change my rotational speed, my flow rate is going to change accordingly. So if I double the rotational speed, I double the flow rate out of the pump. My pressure or head loss, because pressure and head loss are basically related linearly. If I double my rotational speed, I'm going to end up quadrupling the head loss or pressure. And then in terms of the shaft power required to turn this pump, if I double my rotational speed, that's going to require a shaft power increase of 8 times because it feels like omega cubed. Then similarly, if I want to play with the diameter to get some different diameter pumps, so keep my rotational speed omega constant, again, my flow rate is going to go like diameter. Pressure or head loss goes like diameter squared, and power goes like diameter cubed. So where these come from, again, are the dimensional analysis. Looking at my dimensionless numbers, so I can form the grouping flow rate Q over rotational rate, rotational speed omega, and diameter cubed. That gives me a dimensionless number. This dimensionless number I'm going to call the flow coefficient, CQ. And so I can see from this guy that if CQ is constant, that means that Q and omega are directly proportional, just like I have up here. Similarly, I have the head coefficient, which is gravity G times H over omega squared D squared for the head. Again, this is like pressure. So anytime I want to deal with pressure, I can deal with head loss. And I can see here again, these relationships. Head loss looks like omega squared or like D squared. And then my power coefficient, W dot shaft over density, omega cubed D to the fifth. And then finally, my last dimensionless number that I care about is efficiency. So efficiency, basically power out over power in. Power out of a pump is density times gravity times flow rate times head loss. And so rho g QH is my power out. W.shaft is my power into the pump, and so that's my overall efficiency. Another important dimensionless parameter when it comes to pumps. It's what we get from pump curves. Manufacturer is going to give you basically a pump curve, basically tells you how the pump performance data is. So generally given as a flow rate on the x-axis and a pressure drop or head loss on the y-axis. Again, those things are kind of interchangeable. And so basically shows you for some given diameter and some given rotational speed, how that pump's going to react. And so based on different flow rates, what sort of head does that pump produce? And a lot of times you'll have a single curve, so just one line that looks like this. A lot of times you'll have more than one curve. So in this case, I have 3 of them. That basically means that I have either 3 different diameters. So I could have 3 different diameter of very similar pumps. A lot of times the manufacturer will have different versions of the same pump, just different diameters. And you'll have 3 different or some other number, however many diameters they have, different lines for those. Another thing this could be is a different rotational speed. So the same pump, but just a different value of omega. Again, going to give you different performance curves, different flow rate versus pressure relationships. And a lot of these from the manufacturer, you also get efficiency curves. So the efficiency curves kind of look like these blue dashed curves here. With these efficiency curves, they always get better as you go inwards. So maximum efficiency is somewhere down this line here, almost where this red arrow is, but slightly underneath it will be the maximum efficiency. So if I want to run one of these pipes, one of these pumps, I mean, say this pump here, at maximum efficiency, it should be somewhere in this range. So whatever that flow rate is will be roughly the maximum efficiency for this pump. So those blower or fan curves or pump curves, whatever they are, again, for one given rotational speed, one given diameter. A lot of times what we do is we plot that versus the system curve. And so these pump curves, red and yellow curves, usually end up being roughly quadratic. Head loss generally proportional to Q squared. System curves are basically what's going on in the system itself. So really nothing to do with the pump, more of what you want the pump to do. So if you want to pump some water from some location to some other location that could be higher, usually going to be higher, you have to get it to go through a certain length of pipe, has to maybe go through certain curves, certain bends, certain T-junctions, certain valves, all sorts of stuff that adds head loss to the system like we saw last week. So that's basically your system curve. Your system curve is also going to be a function of flow rate and be roughly parabolic, but these are going to curve upwards as opposed to the pump curves which curve downwards. So I have different system curves. I can define that by a baseline curve. So baseline curve being kind of my nominal conditions, what's usually happening. And then a lot of times I could close off some valves and change the system. So I could have different sort of systems that I want to operate through. Could have a system that goes to 3 different tanks, for example. And so I open and close different valves to get to 3 different tanks. And so I have 3 different system curves for those 3 different scenarios. And so once I have my performance curve and my system curves plotted on the same graph, again, usually a lot of times you only have one of these. So one system curve, one fan curve. So if I have just this one fan curve, F1, this one system curve, S3, I can find the operating point. So what's going to happen when I turn this pump on? Again, these system curves, these pump curves are for some particular rotational rate. And so I turn the pump on at that rotational rate. Where the system curve and pump curve meet, this intersection is the operating point. So that's basically what's going to happen at that, using that pump with that diameter and that flow rate to get my water through this particular system, whatever it is. I'm going to end up with a flow rate of whatever this value is. So there's my flow rate of my operating point. I'm going to have a certain head loss or pressure drop of whatever that value is over there. And so that's how I find my operating point. That's how I know what's going to happen to my the water in my system essentially. Now the advantage of having more than one on here is that it's easy to see what happens if you want to change things. So for example, want to change things, I want to go from point A. So I started off with my fan F1, this red curve, and my system S1, this purple curve. And so I'm right here right now, operating at this flow rate, at that head loss. And then for some reason I want to change this, so I want to scale things back. I want to instead go back to point B. So instead of having this flow rate, that's too much, I want to make it slower. So there's two ways I can do this. I can either slow down the pump. So if I slow down the pump, change the rotational speed, I could also technically change the diameter. That's going to give me on a different pump curve. So one way to do it would be to jump to a different pump curve along the same system line. So I didn't change anything to the system, didn't move any valves or anything, move along the same system to get down there. The other option I have to get to this lower flow rate is to not change the pump at all, so keep the same rotational speed, but change the system. So go change some valves to some different things. And that gets me to this other system curve. So same pump curve, but different system curve gets me to that same exact flow rate. Now I have the option of doing both of these to get to that flow rate. Which one should I do? Well, if I look at point B up here, when I changed the system and did not change the fan curve, I ended up with a higher head loss. Whereas the first way, when I changed the pump or fan and didn't change the system, ended up with a lower head loss. Lower head loss essentially translates to lower energy or lower power being added. So lower energy is actually the more efficient way to do it. So if I want to go from point A to point B, that's the way I should go. Change the pump speed essentially, and that'll be the better way to get there. So example of finding the operating point. I have a pump operated at 1170 RPMs, has an impeller diameter of 8 inches, shutoff head 25 feet of water. Same operating speed, so same rotational rate. I find a head of 21.9 feet of water at a flow rate of 300 gallons per minute. I want to find the operating point for this pump. Given this system curve, so again, I have some system. I found that it has this curve, so my head loss varies with flow rate in this manner. A lot of times you see here flow rate in gallons per minute, head loss in feet. So that's just by system, all my pipes and stuff I want to get through. I want to find what this pump performance curve looks like. So I know my pump performance curve is going to look somewhat quadratic, and I have 2 points. So I know my shutoff head, that means that 0 gallons per minute is 25 feet. And I also have the other data point that at 300 gallons per minute, I have a head of 21.9 feet. And then again, I know it should look somewhat quadratic, so my head loss should look like A plus B Q squared. A and B are just constants based on these numbers essentially. So now I just want to fit this equation, values of A and B that fit these two data points. So doing that, A ends up being 25 feet. B ends up being H minus A over Q squared. So 21.9 minus 25 over 300 squared is negative 3.44 times 10 to the negative fifth. And so my equation, quadratic equation for this pump, is 25 minus 3.44 times 10 to the negative fifth times my flow rate squared. And this is in feet when Q is in gallons per minute. So don't have to worry about crazy unit conversions because my graph was in gallons per minute, so might as well just leave it there. The next thing I want to do is actually plot that curve. So here's my new curve, 25 minus 3.44 times 10 to the negative fifth, based on Q squared, system curve from before. And so as I said, the operating point is just where these two guys meet. So that point right there is my operating point. So I'm going to get a flow rate roughly 510 gallons per minute, associated head loss roughly 16 feet, and that's my operating point for this case. as a follow-up, I can want to know now what happens if I change the flow rate for my pump, I mean. So instead of having 1170 RPMs, I want to bump that up to 1450. And now what happens? So for this, I need to go back to my similarity laws. So I have the same pump. So because I have the same pump, have the same diameter, and my two flow conditions are going to be geometrically similar. I also need them to be dynamically similar, meaning I need to have the same values of all those dimensionless parameters we saw before. So things like the flow coefficient. My flow coefficient was Q over omega d cubed. So for my new case, Q2 over omega 2 d2 cubed has to equal to my original case, Q1 over omega 1 d1 cubed. Again, diameters are the same, so those go away. Solving this for Q2, I get Q1 times omega 2 over omega 1. So again, we see kind of a linear relationship between Q and omega, like we saw at the beginning of this lecture. So now with that, what I can do is I can find my new flow rates. My first flow rate, first data point from the previous example was 0. So again, it ends up being 0. Second flow rate of 300 gallons per minute. Can scale that guy, omega 2, 1450 RPM over omega 1, 1170 RPM. Gives me a new flow rate for that second point of 372 gallons per minute. And then I want to do the same thing for my head losses. Head losses, look back at the head coefficient. Remember that guy, CH, was GH over omega squared E squared. G doesn't matter because gravity is going to cancel out the same. And then again, D cancels out. So basically what I'm left with is H2 is H1 omega squared over omega 1 squared. Again, that squared relationship for the head loss or pressure that we saw at the beginning. And now I want to find the two new head losses. So I have two head losses from the first example, one of 25 feet, one of 21.9 feet. So the one at 25 feet, again, scale that, 1450 over 1170, whole thing squared. Gets me a new head loss for that scenario of 38.4 feet, and that's going to be at 0 gallons per minute. The other head loss at 21.9 feet happened at 300 gallons per minute. Again, square that or scale that guy by the same factor, 1450 over 1170 squared. Gives me a new head loss in that case of 33.6 feet. So that's going to be my second data point at the new flow rate of 372 that we just found. So in this case, I have two data points, or two new data points, 0 and 38.4, and 372 and 33.6. You want to fit those to a very similar quadratic. So H is A plus B times Q squared. This case, I actually get the same value of B, but get a different value for A, so 38.4 now. And so now I'm going to plot this guy on the same system curve. I actually have the same, here's my old pump curve, old system curve. And then here's this new one. So this is the 38 minus 3.44 Q squared. And so again, you see the base has the same slope, just kind of pushed up, roughly 13 feet. And so a new operating point, this guy right over here, has a new flow rate of roughly 630 gallons per minute, new head loss just under 25 feet. And so that is my new operating point when I increase the rotational speed of the pump. And so next thing we want to do is deal with more than one pump. So we saw, again, last week, what happens when we have more than one pipe in parallel and series. We can also have pumps in series and parallel. So what we want to do with this is instead of having three different pump curves on the same graph, we want to basically translate these systems into a single equivalent pump. So instead of having three pumps in series, for example, kind of replace that with one big pump that provides the same flow rate and head loss. And that way we can have just one single pump curve that we can use to find the operating point. And so to do this, we need to know that for pumps in series, just like pipes in series, they're all going to have the same flow rate. So again, nowhere else for that flow rate to go. So it all has to be the same flow rate through all my pumps in series. The total increase in head or pressure will be the sum of all the individual pumps. So each pump is going to give a certain pressure rise. And so through all the pumps, I just add all the pressure rise together to get the total. Again, at that same flow rate. Parallel is going to be kind of like the opposite. All have the same pressure difference, but the flow rates are the sum of all the individual pumps. And so that's all I really need to be able to combine these into a single pump from my parallel network series. So in terms of the series pumps, as I said, the heads are added at a constant flow rate. So if I have a given flow rate, I just want to take that and then add the two heads. So if I have this single pump and then I have two of them, I want to put them together in series, I'll take a given flow rate, find its head value, whatever that head value is, multiply by 2, and then that's my new head value for that same flow rate. Perhaps better is take two different pumps, so pump A and pump B. Pump A has a head given by this number here. Pump B has a number given by that value there. If I take these two head values, add them together, that's going to be my head for my equivalent pump, so A plus B together in series. I just take my two head values, add them together, and that works at any flow rate. So this flow rate over here, I just take this value for A, that value for B, add them together, and that's this value for my equivalent pump. This guy here, same value, so multiply by 2. That's my value for the equivalent pump. This value over here, pump A plus pump B gives me my equivalent pump value. So same flow rate, add the two heads, that gives me my equivalent pump curve. So this way I don't have to deal with these two curves. I just have this one equivalent pump. Similar but opposite in parallel. So parallel, I have the same head, but add the flow rates. So in this case, instead of having a constant flow rate and adding the heads, I have a constant head and add the flow rates. So again, if I have one single pump and I want to have two of them placed in parallel, I find certain head value, find the flow rate, and then double it, and that's my new equivalent pump. So again, if I have two different pumps, pump A and pump B, some certain head value, flow rate for pump B, flow rate for pump A, add those two numbers together, and that's my flow rate for the equivalent pump. Somewhat interesting thing happens here. If I'm looking above where pump B is, so somewhere up here, at this head, pump B doesn't add anything. So because pump B is not doing anything, my equivalent pump is the same as pump A, because pump B hasn't done anything yet. Then as I come down, once I get below this point, pump B starts doing something. So now pump B starts adding to pump A. So now this equivalent pump curve deviates from my pump A curve because pump B is actually helping now. So this, again, this is my equivalent pump curve. In this case, pump A and B in parallel. The last thing today is an example. I have two Goulds pumps placed in parallel, both of which are model 1.5 by 3-7 3198 and run at 3,500 RPM. So here's my manufacturer curve for 3,500 RPM for this particular Goulds pump. You can see here, again, I have 5 different performance curves for different diameter pumps. So 5-inch, 5.5-inch, 6-inch, 6.5, and 7. So these are really the only curves I care about for this example. Again, we have some like efficiency curves and things, but again, these guys here are the ones I care about. In terms of this example, I have one with a 7-inch rotor, so this line here is going to be important, and then one at a 6.5-inch rotor. This guy here is going to be important. So those are my two pumps in parallel. I want a flow rate of 250 gallons per minute, and so therefore I want to find the operating point. So I want to take these two curves and basically add them together in parallel, get my equivalent pump curve, and then find the flow rate. So here's my 7-inch curve, here's my 6-inch curve, and then again add them together in parallel. So that means I want to take values at heads and add them together for the total. And so above here, nothing happens. And then once I get to here, the 6.5-inch pump starts doing something. So I deviate from that 7-inch curve and get this equivalent performance curve. And so all points here, I just take that guy, that number there, that flow rate, add that flow rate, and I get the total flow rate. Now I want a flow rate of 250 gallons per minute, so roughly here. So I want this to be my total flow rate. So I want that to be my point. And so in terms of these two pumps, I'm going to have a flow rate of about 160 for my 7-inch pipe or pump, I mean, and then a flow rate of roughly 90 for my 6.5-inch pump. So 90 plus 60 gives me my total of 250. So therefore, my operating point for these two pumps should be 90 gallons per minute for the 6.5-inch diameter pump, 160 gallons per minute for the 7-inch diameter pump, and overall gives me a head loss of roughly 175 feet, as you can see from the graph. So that's it for today. Hope this wasn't too terrible. Feel free to ask questions either in office hours, so every day, 3:30 to 5, through these Zoom meetings, or you can also go on the discussion board on Blackboard and ask questions there. There'll be sections for each lecture, a homework project, everything else. So feel free to interact on those, and I will see you next time.